I'm Zev Weiss. I'm here presenting our paper ANViL, Advanced Virtualization for Modern Non-Volatile Memory Devices. This is work done in collaboration with the team at SanDisk, including Sriram, Subramanian, Swaminathan, Sundararaman, Nisha, Talagala, and my advisors, Andrea and Remzi, Arpaci-Dusseau at Madison, where I am a PhD student. So it's just sort of a high-level first-cut overview. ANViL is a block storage virtualization layer. It presents a traditional block interface plus a set of 3 additional address remapping operations that, when combined, offer the ability to easily implement a number of useful storage features, including file snapshots, volume snapshots, deduplication, and what we call single-write journaling. So to start with, virtualization as a concept we're probably all familiar with has been applied to a number of different resources in computing systems over the years, perhaps most notably to memory, virtual memory enabling a lot of useful things like efficient implementation of the fork system call, shared libraries, mmap, zero-copy I/O APIs like splice and so forth. But storage, while conceptually very similar, it's essentially just a flat array of locations that you can store and retrieve data to and from. Virtualization of storage has remained generally much more limited, with existing storage virtualizations primarily focusing on administration and management sorts of features that basically operate kind of at volume granularity and are less directly useful to applications and users. So our goal here is to provide block storage virtualization that is more fine-grained and flexible and in general, kind of more general purpose. So to that end, we're presenting what we call advanced storage virtualization, which fundamentally revolves around a logical to physical address map, which is much more like the address map involved in virtual memory. It's block granularity. It allows many-to-one mappings, and critically can be directly manipulated by the host system. So having this available enables a number of useful features, as mentioned earlier, things like file snapshots that are very easily implemented, require very little modification to existing file systems, optimized journaling transactions, volume snapshots, and deduplication. So to do that, we extend the traditional block read-write interface with 3 new operations, range operations, clone, move, and delete, which respectively copy, move, and delete data just by manipulating an address map. So to look at those in detail, the clone operation starts out with a source extent of blocks that are mapped to some underlying physical space. And after applying a clone operation, you end up with an address map that looks like this, with multiple regions of logical address space mapped to the same underlying physical storage. Now, these mappings are treated in a redirect on write fashion, so that when a write comes in to a shared mapping, it gets redirected to a new location so as not to affect the data visible via any other mappings to the same blocks. A move range operation is a similar sort of thing. You start out with a source range of logical blocks, and you give it a destination range, but it does not leave the existing mappings in place. It simply relocates data from one logical address to the other. And finally, delete operation is generally similar to existing trim and discard commands in current systems. It deletes data by removing mappings, but unlike trim and discard, it is strict and is not merely advisory. It guarantees that as soon as the delete completes, those blocks will read as 0 from that point onward. In addition to this, we provide a few extra properties to just sort of make the system more generally useful. For one thing, range operations are immediately durable. They're synchronously persistent as soon as they're acknowledged. We provide a sparse logical address space. It's thinly provisioned, which is necessary in order to actually make use of the physical capacity you have in the underlying device in the presence of a many-to-one address map that you get with the clone operation. And finally, we offer atomicity. You can take a batch of these range operations and submit them as a single atomic vector with the guarantee that in the event of a crash or power failure, either all of them or none of them will take effect. So we've implemented this in a prototype system we call ANViL, the Advanced Non-Volatile Memory Virtualization Layer. It takes the form of a stacking Linux kernel block device driver. It is not a flash translation layer, nor is it built into one, but it resembles one in a number of ways that I'll describe in a moment. Presents a 48-bit or 128 petabyte logical address space and maps that onto the presumably much smaller physical storage that you run it on top of. And it provides a basic block interface plus our 3 range operations, clone, move, and delete. Its implementation is like an FTL, internally log structured. It writes data in large sequentially written segments that are 128 megabytes, always to a new location. It never overwrites in place. And also similarly to an FTL, we have a background garbage collector to manage space. Reclaiming blocks one at a time when they become unmapped isn't really a viable approach for us because we need to write segments sequentially. So we need to reclaim entire segments. So the garbage collector in the background scans for underutilized segments with relatively little live data in them, copies those blocks forward into a new segment, and then reclaims entire segments in a single go. So to illustrate the utility of ANViL, we have a set of case studies. The paper describes volume snapshots and deduplication, but in the interest of time, I'm just going to focus on the first two, file snapshots and single write journaling, which I think are probably the more interesting ones to look at. So file snapshots, and I should clarify here, just terminologically, perhaps I maybe should have called these file clones. I realized a little too late that snapshots can imply that they are read-only. That is not the case here. These are fully writable, normal views of data. So we've modified ext4 with a special I/O control that, given a pair of files like so, with file A and file B mapped to a distinct region of the logical address space of the storage device used by the file system, in that case, that device is ANViL, and ANViL internally remaps those to separate, distinct regions of the actual physical storage. This I/O control that we've added to ext4 allows you to perform a file clone that ends up giving you this, with those two files ultimately mapped to the same underlying storage space. And this can actually be easily extended to provide deduplication as well. So the implementation of this was relatively simple. It took a few hundred lines of code added to ext4. Just for a sense of scale, it's about 1% extra code added to the existing code base. In comparison, Btrfs, which is designed from the ground up to support this sort of thing, in addition to other things as well, is over twice as large at about 83,000 lines of code. So to look at its performance, we have here the elapsed time of a simple file copy implemented by the standard cp command for various file sizes. With a cold page cache, this is run on a Fusion I/O drive, so you can get a few hundred megabytes, maybe a gigabyte per second of bandwidth here. But a 2 gigabyte file takes about 7 seconds to copy. Run it again with a warm page cache, it takes about half as long, as you might expect. And then if you implement this with our ext4 ANViL specialized I/O control, it might be kind of hard to see there, but there is a tiny sliver of red down there at the bottom of the 2 gigabyte graph. It's about 100 times faster than the cold cache CP for comparison, basically allowing you to transform an operation that's proportional to the size of the data involved to instead one that's proportional to the size of the metadata. So obviously a big speed up there. Our other case study is what we call single write journaling, which is an optimization of conventional file system journaling that we're probably all familiar with, but just for overview. If you have a set of modified blocks, conventionally you write those blocks to the journal area of the file system as part of a transaction with a start and a commit block, and then later rewrite those blocks to their home locations in the main file system. So you end up writing those blocks twice. What you can do with ANViL instead is to, given your modified blocks, write them into the journal. Note that it's not really, it is effectively part of a transaction, but you don't need to explicitly record it as a transaction. Note that there are no start and commit blocks here. Once it's in the journal and ANViL has remapped it to the underlying physical storage, you can then simply perform an atomic range move to relocate those blocks to their home locations. So you end up getting the same resultant state, the same atomicity guarantees, but you don't have to write everything twice, and you don't have to write your start and commit blocks in the journal. Sorry, that was supposed to happen a moment ago. Implementing this, we also did it in ext4 by modifying the JBD2 journaling layer. It required adding about 100 lines of code, but also in turn allowed us to remove about 900 lines of code, so it's ultimately kind of a net simplification of the file system. Looking at its performance, we take write throughput at varying write sizes in data journaling mode. This is the normalized throughput increase. So we see that obviously the general trend here is that at smaller write sizes we get a larger gain, and at larger write sizes the gain is relatively smaller. There are a couple of reasons for that. The first is that with smaller writes you end up with smaller journal transactions, and thus the savings you get from being able to omit the start and commit blocks of every journal transaction are proportionally much larger. So here we get almost a full doubling of throughput there. At the opposite end of the scale, with larger writes and a larger absolute throughput, what ends up happening, especially on faster storage devices like we were running on Fusion IO drive here, is that your throughput ends up getting bottlenecked by JBD2's single-threaded journal commit, which has a single kernel thread that serially writes out all transactions to the journal. So that ends up sort of holding up performance at the high end there. But nevertheless, in all cases, we get significantly improved performance, reduced write traffic, and thus increased flash device lifespan. So in conclusion, ANViL, by offering 3 new block interface operations, clone, move, and delete, enables easily implementing a number of useful storage features, such as snapshots, deduplication, and optimized file system journaling with a single write. And in general, it provides a nice, simple, clean interface to a powerful storage foundation. So thank you, and I will take any questions.
Joris Wills, Dell Storage. How do you handle tracking, how do you free the physical space when you can have multiple logical guys pointing to it?
So the garbage collection is a significant bit of extra work. It is significantly different from more conventional FTL garbage collection, obviously because of the many-to-one mappings. What we have it do is basically, it scans through the metadata, records blocks. It's complicated, but basically it does a somewhat brute force approach and scans for unmapped blocks. When it finds segments that are relatively, empty of live data, it takes the remaining live data and copies it forward, and then.
So you're looking from the top down, not back up.
Exactly.
You're not doing ref counting or something like that.
Correct.
So Christoph Helvig here. First, a unfortunate correction. So trim is only advisory. It's
right.
Creating us all kinds of problems.
Sorry, I may have given the wrong impression there. Ours is unlike trim.
Oh, okay.
Ours is strict and guarantees zeroing.
Okay, good. And the other one is, how do your clone semantics differ from the various T10 Xcopy variants? Is it basically the same, or do you have any more interesting semantics?
I'm not intimately familiar with those. I think it's probably semantically similar.
All right.
But I'd like the expertise to say with certainty.
What is the device in the backend? Is it SSD or storage class memory?
Sorry, is it SSD or what?
What is the target device in the backend?
It's oriented towards non-volatile memories, flash storage particularly. Mostly, it aims for sequential writing for friendliness to flash. It also, the garbage collection previously mentioned, would be relatively unfriendly for a disk due to random read access. So it is broadly targeted at flash storage.
So both of the backend device and the front end, it also has a.
Sorry, I couldn't hear that.
So flash device in the backend also has a logical physical translation layer in this system.
I'm sorry, perhaps I should talk to you offline.
So there is a 2-layer of logical physical translation layer in this system.
Yes, sorry. It is not an FTL. It does not deal with raw flash. It deals, the underlying device is a standard block device interface. So if it were running on flash, there would be an actual FTL underneath it.
Oh, okay, thank you.
Sorry.
What's the space overhead on storage and the space overhead in memory? So on storage or somewhere, you've got to keep your translation layer. So is it 8 bytes per block or 32 bytes per block? So
right.
That's one question. And the other one is, what's the memory cost of the garbage collection? As a if you have lots and lots of storage, then garbage collection is going to be potentially expensive in space.
Yeah. So the overall metadata space overhead is, I think, like low single-digit %, 1 or 2%, I think, for the forward address map. Garbage collection is. Because of what I mentioned earlier, the sort of top-down view it takes, the garbage collection overhead can actually be sort of scaled at will in terms of its space consumption. It's not actually tied to the capacity due due to the way it approaches gathering its information. I can explain that to you individually if you'd like to hear more about it, but the GC space overhead is not a big issue.
All right, let's thank the speaker.